So, first thing. Let's do that. You guys know what a polygon is already? Take a guess at it? Shape? Be more specific here. Shape. Like here's the thing. You say a shape. I mean, I can draw this right there and be like, oh, that's a shape. Is that a polygon? There's, I got it. Okay, so the shape of the side. There's the side. There's the side. There we go. Might not have to have equal sides. But now here's the thing. Okay, don't have to have equal sides. It has to have a straight side, but it has to have, you just said, all the sides have to be straight lines. It's a segment. You can't have any curved parts be classified as a polygon. That doesn't make it not a shape. I mean, I can still create a shape with curved sides. But to technically fall under this realm, it's essentially got a shape with segments for sides. No curved parts. Okay? Also, if I did, like I'm going to have the full thing up there, but also if I did one with straight sides and I did like this right here, I mean, would that be a polygon? No. No, why? They're not fully connected. Everything has to be connected. What if I did that? And I said, look at this entire thing. Is this entire thing classified as a polygon? No. Because you've got kind of an overlap. Okay? This part of it would be technically a polygon, but if I said, look at the entire thing, you couldn't classify it. So, by definition, these are the two conditions. But here's the thing, guys. I'll put the definition up there, but if you just remember that you can't have any curved parts on it, and it has to be fully like enclosed, no gaps, it has to be all the way connected, you know what a polygon is. All right, this is just technically the formal definition. 3 or more segments. For us to have a actual polygon, there are, in theoretical forces, things less than 3 sides that exist. You guys don't deal with that stuff in the air, so you don't have to worry about it. You don't want to. So 3 or more segments, okay, which are the sides, which you kind of told me anyway. And when it says no 2 sides with a common endpoint are collinear, I mean that just means that you wouldn't have one side classified as this. Like if that was a polygon, like this whole thing would be a side, not one side and 2 sides, if it was a straight line. That's kind of what this common endpoint thing is. Like this would be your common endpoint, okay? So it's just saying if this whole thing is a line, if you put a point on it, that doesn't create more sides. All that does is put points on the side. And then the other thing is dealing with the gaps. Like each side intersect exactly 2 other sides. That's dealing with the not having gaps or overlapping parts or repeated sides or things curved around, that kind of thing. But, like I said, if you already know that you have to have straight sides, nothing curved, and you have to have no gaps in it, everything connected, you know how to identify it all. Okay? All right. Now, so that would be a basic. All right, now, outside of understanding that the segments are a side, which are in the definition, and at that point where they come together is called a vertex. The main thing, or the first part of today is going to be dealing with classifications. Okay? Generally, guys, the classifications are what people tell me when I say name this polygon. Like if I told you to name this polygon, what would you probably name it? Okay, pentagon's a classification. All right? So the classifying is, like I said, what you guys already think in your brain as naming it. If I said name this, when you name it, you always name shapes with the vertices. Just like when we did triangles. If you named a triangle, it was like triangle ABC. So if I name this, the name for this would be like PQRST. All right? Or really any order of these, as long as they travel in a manner such that like the letters next to each other are kind of adjoining vertices. Like I could do RSTPQ, that would be another name for it. Do RQPTS, any of these right here would be names for that polygon. So guys, just understand, if I ask you to name it, I'm telling you to identify it by the vertices. Saying that the pentagon up there would be a classification. Okay. Now, the whole pentagon thing, triangles, and even like four-sided stuff. Most of you guys are familiar with all of those already. You might have forgot a couple, or you might not know a couple. You guys are going to be responsible for knowing how to classify polygons with 3 sides, 4 sides, 5, 6, 7, 8, 9, 10, and 12. Okay? Now, you don't know all those names. Go through them now. Okay? So, this is dealing with the first classification. This isn't the only way you classify. Okay? There's other things that also go along with it. So starting with this, obviously 3 sides we've already dealt with. You know that's a triangle. 4 sides, you guys know the name for a 4-sided polygon? Remember, it's general too. Square, quadrilateral. Square is a type of 4-sided. Rectangle is also a type. Okay? So in general, anything with 4 sides would be a quadrilateral. That's why quad always means 4. Okay, that's the prefix for it. 5 sides was just up there. That was your pentagon. The 6 sides, hexagon. About 7. That was what? Heptagon. Stuff like that. Big mistake on this one is a lot of people do septagon for some reason. I don't know why. It starts with an H, but it's heptagon. About 8 sides. What's that? What? Oh my gosh. I know. I want to say it again. Can't say it. Come on. Well, now we're all curious. What is that? Just assume it was something really bad.
Yeah. I thought you were like, if it's like reminded that stuff there.
You'll have to notify the top.
Well, not right now.
No, not until that's chapter 11 again.
Oh, so not that far away. That's like next chapter, right?
Alright, next one, 9 sides is a nonagon. Nonagon, right. The negative of gon. 10 would be your decagon. Okay. And then, guys, the only other one that you have to know is that. Okay. 12 stuff. These are the only ones you guys are responsible of knowing. Like, this is going to be required of you to know the names of this. There'll be reference throughout the book. Alright? This is, in general, most geometry books I've seen in high school stick strictly with you having names for that set up there. Anything outside of those numbers, all right? I think I have it up there. I gotta write it out. Anything outside of these numbers, guys, is called an n-gon. Okay. Now you don't say n-gon. The n equals the number of sides. So if I was classifying like a 20-sided polygon, for you guys, you just say it's a 20-gon. Okay? If it was like 30 gon. For you guys, if it was 11, you could say 11 gon. Now, obviously, there are names for the rest of them. Just because everyone asks every year what they are, I have a printed out sheet that always has them on there.
Oh my
Yeah, it's like everyone's right here.
I'm pretty sure I leave my big one.
Yeah. So here's the thing, guys. Like the reason I started doing the list was mostly for the fact that everyone always asks about 11. And the only reasoning I could assume that the book has for never including 11 is there are multiple names that I found for 11. Like decagon is usually the one I see the most, but also on there you can see there's a hendecagon that would also fall under 11. So my assumption is since they have multiple, the book just says, the heck with it, and I don't feel like dealing with it kind of thing. But everything else beyond that is set up. Now, I told you guys, you are responsible for the ones that are up there that we've done. Okay, the 3 through 10 and then 12. But I will have an extra credit question on the test relating to the other names on there. Okay? Yeah, I'm going to put a 10,000 one on there. Get her near again. What? 86? Now, I would give you one like maybe 54. You'd have to say pentacontachi tetragon.
Why do you have to use the word chi?
Chi is like a linking word for this. Like if I did 54, pentacons would be your prefix. Chi is linking it to that. So you're doing 50. Chi is like the and part. So it's 50 and 4. It's kind of like, when you start counting in Spanish or something. Yeah, well, then they get in other languages. They do yeah, it's just like linking things here. Yeah.
I thought we were supposed to put like the end song thing, like 19, put like 19 songs.
Yeah.
So then why?
Because everyone asks about.
We don't need to know
I will have an extra credit card. So it's, if you want to, because it's a real basic method to it, you just don't have to.
Is that like a link to like all of them to use that for everyone?
When like the extra credit one I do will be, I'll be on my own. Because, I mean, if you look at them, 20, 30, 40, all those, they have the same prefix as that. Like 50 has a penta in it, 6 has a hexa in it. All right, the prefixes don't ever change. 8 is always going to have octa in front of the phrase. Okay? That's why when we get to solids, there's actually a octahedron also, which just means it's a solid with 8 faces. So octa will always mean 8, regardless of where we're at. All right, so anyway, yeah. Okay. Next thing. So again, still, we're only dealing with classification right now. The words that were up there, it was all classifications. Okay? The next classification you can put on to a polygon is either going to be convex or concave. All right? Does everyone know what these words mean right now? What?
It's like, if it goes in, then it's like concave, and if it goes out, it's convex.
There you go. That's all you got to kind of remember. If it goes in, it's concave, goes out, it's convex. All right? So out of the 2 that are up there, if I said which one goes in, would it be the one on the left or right? Left. Okay, because you got sides that kind of cave in. Hence the word concave. Left, my right, and left. This is the concave one. All right, and this would be your convex because you don't have anything caved in. Okay, so if you cave in a side, then it's concave. That's basically what it gets down. All right. Now, like there are tests for this. The big test is whether or not something is concave. The test is essentially you take the sides, you extend them out. If you extend the sides and it passes through the interior, it's technically concave. But it's generally easier for people to just remember if you got something that goes in, it's concave. Okay? So if I did like up till now, if I did like a full classification on these, this would be a concave octagon. Right, because there's 8 sides there. 1, 2, 3, 4, 5, 6, 7, 8. And this would be a convex pentagon. Okay, so just kind of remember, guys, write it in your own words with this. It helps a lot if you do. If you try and go to the book and get the formal test for it, it usually confuses more people than it helps. Okay, so this is a lot easier to write in your own words. So this is the second. So first classification is number sides. Second classification is this, convex, concave. The only other words you guys will put on there in terms of classification are these things. You have equilateral. I didn't include equiangular up there. I mean, that absolutely exists. And then regular, not the type. All right? Equilateral you did with triangles already, guys. Word means the same thing with polygons of bigger sides than 3. Okay? Equilateral triangle meant what? Like if I said a triangle is equilateral, that meant what about this side? They all sides are equal. So if I said I have an equilateral like heptagon, it still means all sides are equal. So that never changes. So if I had a shape right there, right, this would be a, how many sides are there? 6. Is it concave or convex? Convex, right? Because there's nothing caved in. So this is a convex hexagon. All right? And according to the way I have it marked, all the sides are marked congruent. So I can say this is a convex equilateral hexagon. Okay? All right, so equilateral still means the same thing. All sides congruent. Next one, equiangular. Like we probably didn't talk about that much, but equilateral triangles are technically equiangular. That just means all the angles are the same. Okay, and guys, once you get beyond triangles, it is possible to have a polygon that is equilateral and not equiangular, and vice versa. Like I can have all the angles marked congruent, but all the sides aren't congruent. All right, same thing up here. All the sides are congruent, but the angles aren't necessary. The only one where it definitely has to occur is a triangle. Like triangle, if it's equilateral, all the angles are also the same. But beyond that, it is possible to have one without the other. All right, but if you do have both things happen at the same time, if it's equilateral and it's equiangular, it's regular. So anytime that word regular polygon comes up, or that phrase, that means that all the sides are the same and all the angles are the same. So all of these up there are convex hexagons, because they all have 6 sides. The difference is that top one's equilateral, middle one's equiangular, the bottom one is both of them, so you say it's regular. Okay, so anytime from now until the end of the book, this word will pop up a lot. When they say it's a regular shape or regular whatever we're dealing with, that means that all the sides and all the angles are exactly the same. Okay, and that's going to tie into finding the angle measures here in a second, because the next part of this is going to be dealing with finding the actual numerical value for the interior angles and then even the exterior angles. Okay, so let's say it's the number part of today, if you want to classify it that way. All right, I'm going to go past this. Yeah? Okay, so first, dealing with the interior angle, right? Interior angle still means they're inside the shape. All right, and everything, I don't probably have it written up for every little thing, but all the formulas that we have up here are only in reference to convex polygons. Okay, this stuff doesn't work with concave ones. All right, so for all the formulas, guys, just keep in mind it's all convex polygons. All right, that's the formula you use if you ever want to find the sum of the interiors. Okay, essentially what this comes down to is that if I took a polygon, you can see I draw, if I'm doing examples, I draw pentagons a lot because they're easy to draw. But the idea of this formula is 180 degrees. We've seen that before because 180 degrees, guys, is the number of degrees in a triangle. And you take the interior angles of the triangle and add them up. The n-2 part, this is essentially the number of triangles in the shape. Such as if I took this pentagon and I drew this line right there. And this line, guys, coincidentally, that line right there, it's called a diagonal. Okay, a diagonal just connects two vertices together. All right. So now I didn't have that specifically as a definition, but you will need to know that word. All right. But if I drew in all the diagonals from this one vertex, essentially what I'm doing is I'm breaking that pentagon up into 1, 2, 3 triangles. So that means that every triangle, interior angle-wise, has 180 degrees in it. So I know there's 180 there, there, and there. And this pattern works for every single polygon, okay, that you can draw out. The number of triangles that are in there are always going to be 2 less than the number of sides. Okay, and it's the whole formula goes by number of triangles times the sum of the interior angles of the triangle. It's always n-2 times 180. Okay, so like for that one, yeah, that'd be 5. Okay. Now, this formula, guys, is mostly used for maybe like solving for a variable when I give you x's and y's on the angle measurement. That kind of thing, that's how it's going to come up. I could even give you a basic problem where I say, look, a polygon has like, 50 sides. What's the sum of the interior angles? And you just plug 50 into the formula. It's just a matter if you have to remember the formula. And make very clear on your paper somewhere that you understand that this is the sum of the interior angles. Like make sum very prominent on it. Because you're going to have a formula here in a second, and we get to it, where it's going to be the measure of one interior angle. Okay, so just understand, sum and one are completely different things. All right. So these would be your basic problems. So say, okay, find the sum of the interior angles of a convex, non-Polygons, and 17. This is the easiest problem you'll do with these, because there isn't any work to it outside of the fact that you have to recall that formula when you get to it. Of course, like right now, we just did that formula, like I just had it up there, so it shouldn't be that big of an issue. But, when it comes to test time, like you're going to have to get in your brain sum of the interior angles equals that formula. All right? It's all a matter of recall. Again, it's not difficult stuff. Okay, same thing as like that last chapter. Really, the stuff wasn't difficult, but there's a lot of recall involved. All right, so if I was doing this, I would have to go, okay, non-Polygons, 9 sides, 9 minus 2 times 180 is whatever my answer is. What is it?
1,000.
All right, and then this one here will be 17 minus 2 times 180, which is something. Something? What is that? Something. What is it? Yeah, 27. Okay. Alright, so the problems aren't necessarily going to be difficult with this, guys, but it's just a matter of you need to be able to know how many sides are in the name, and you need to know which formula you use. Again, key word here, sum. Okay? Alright, now, if I move to exterior angle, alright? Come back there. Okay, if I move to the exterior one. Exterior angles, guys, always add up to 360. We actually talked about this when we were doing exterior angles of a triangle, probably back in chapter 4. It's been a little while.
Is this one for convex too?
This is all convex. Everything here is convex. The whole idea is in the exterior angles are the ones that are labeled up there. Okay, the ones that are referenced as adding up to 360 are the ones that are drawn up there. Okay, and we talked about this. I said, if I took all of these and broke them apart, like if I took angle 1 and broke it apart and put it next to angle 2, and put those next to angle 3, angle 4, and angle 5, they're always going to make a circle. Like it would always be like 1, 2, 3, 4. You'd have like angle 1 there, 2 there, 3, 1, 5. And it doesn't matter how many sides they have. The only thing that happens is as you increase the number of sides, these angles get smaller and smaller. That's all that's going to happen. Okay, but the fact that these will always break apart and make a complete circle, which is 360 degrees, right, in a circle, they're always going to be the same. It's always going to be 360. And this is, again, guys, sum. Okay? So if I said, like, find the sum of a convex, the exterior angles of a convex, like 200 gone, it would be 360. There's any work with it. It's just a matter of you remembering. Some of the exterior is 360. No formula, no nothing.
So
Just 360.
we would do that for concrete. And when we do for the in my series times 180, it's convex.
Everything's for convex. All right, now, next. Next thing, okay, so this stuff here is going to move more into the realm of the one angle and the one exterior angle. Okay, as opposed to the sum, like I was saying, try and make sure you make sum prominent, and with this stuff you're going to make one prominent. Okay? Now with regular polygons, like by definition we already did it, right? They're equilateral and they're equal angular. Okay, so I know that all the interior angles are exactly the same measure if I say a shape is a regular polygon. All right? Which means in this case I could give you like a regular polygon, 7, 8, 9, whatever, how many sides? I can say I want you to find one interior angle of that regular polygon. You can. And all it is a matter of taking the sum formula we already did and dividing it by the number of sides. Because the number of sides and the number of angles are always exactly the same. Okay? And when you want to find one interior angle, you're always going to take what they add up to, which is the sum, and divide it by however many things are up. Alright, so what you need to do is, again, make sure next to this you write like something like measure of like one interior angle. Okay, just so you don't confuse them. For some reason, someone's always going to do, if I say find the sum, they'll do this one. If I say find one, they'll do just the top one. Okay, either because they're not reading the directions correctly, they think they know what the question's going to ask, or they just labeled these wrong. They didn't make it prominent enough that they know which formula goes for the sum or which one goes with one. So make it very clear in your paper, guys, which one goes with. And then, of course, I can do the exact same thing for an exterior angle by still doing sum divided by number of sides. Just in this case, right, the sum of the exterior, like we just said, is always 3/6. So with both of these, make sure you're very clearly labeling this is for one angle there. This is for one angle. Okay. Can I go past this guy? No? All right. Trying to think. I hope I got an example. But I'm going to go back and do, there's an example I skipped through that I am going to go back to. And there's one other thing I want to point out here. Kind of skipping around a little bit. You're still right now. I'll pass by this here again in a second. Okay, so the types of problems you'll see, like this will be an example of one, where it's just a basic solve for X problem. It's not even really that complex because they literally just have X on an angle, and they give you measures for the rest. But the way you approach any problem like this is going to be the same, because what you should notice, like if you saw a problem like this, guys, you should notice that 88, that's an interior angle. That is. All these are interior angles. And in the formulas we've dealt with today, right, we're dealing with finding interior angle measures for these convex polygons. And that's a convex polygon, so I can apply what I was doing. All right? So basically, any problem like this where they're giving you angles inside, they're saying solve for X, or solve for the variable, Y, Z, don't care what the variable is. Basically, all you're doing is you're finding out what the sum is. You're setting it equal to the sum with the numbers given. All right, so on one side, you're going to do the sum formula, and on the other one, you're going to actually add up what's in there. All right? And if I added all those together, someone add those up. I don't know what they're doing. 88 plus 142, 105, 136, all that stuff added together. And then, guys, on this side, obviously there should be 6 sides there. So 6 minus 2 times 180 should get you how much? What's 6 minus 2 times 180? Four times 180. What is it? What? 7 1. All right, and then yeah, you would subtract it over to get 1. Here's the thing. Someone asked, you know, for this problem, you wouldn't want to do this formula. Just to point out, if someone else asked, this formula, guys, remember, is only for regular polygons. These angles are all different, so I know it's not a regular polygon. So I couldn't just do that formula. Okay, just so you distinguish between the two, this is only for regular polygons. Okay? All right, now, get back to where we were. All right, now, if it was a regular polygon, I would give you a problem like this. Okay? And I would know, for this problem right here, I know that if I wanted to do it, I would be using that formula, and I would be using that formula. Okay, because I've got interior and exterior, so this is my interior, that's my exterior. I know it's a regular polygon, so I can use this. And I also know here it says find 1. 1 is always the key thing here. 1 and regular are the key words. So really, the only thing I have to do to complete this problem is find out how many sides the dodecagon is. Which, how many sides does the dodecagon have? 12. Right? So my interior will be whatever that is. Exterior is whatever that is. I do not know what those are. Well, I probably do, but someone would calculate do more. So what is this here? 10 times 180, which is 1800. Correct? Divided by 12. Over here, 360 divided by 12.
Wouldn't that be 30?
30?
Okay.
I think that's correct. And what about this one? 150? Okay, so those would be your two answers. Again, guys, the problems aren't that difficult formula-wise, but it's just a matter of recognizing when to use which formula. Like these right here, only come up if it's one angle and it's regular. The one before that, I was technically finding one angle, but it wasn't regular, so all I was doing was the sum. All right, that's the trick to these, making sure you pick the correct formula. Okay.